This is part 3 of the lecture covering basic vector mathematics. Now we begin to take a look at two-dimensional vector addition. Go ahead and access the next problem on the handout called Lecture Examples. Go ahead and copy it down into your notes. Okay, let me read the problem to you. We're to find the magnitude and direction of the resultant of the following two vectors. Okay, vector A has a magnitude of 5 meters and it's at a 45-degree angle. Vector B has a magnitude of 3 meters and it's at a 135-degree angle. Those angles, by the way, are with respect to the positive x-axis. Okay, so A is equal to 5 meters at a 45-degree angle. B is equal to 3 meters at a 135-degree angle. We're going to find the resultant. We'll call it C. This is equal to A plus B. Okay, now how do we go about adding these two vectors together in two-dimensional space? Well, so far, graphically, the only means that we have available to us is the tail-to-tip method of vector addition. So like I did in the one-dimensional case, now in the two-dimensional case, I'm going to go ahead and add the vectors together in that manner. In the one-dimensional case, because I was just drawing out a number line, it was perfectly fine for me to just go ahead and draw out a rough diagram as you saw me do. However, in this case, with this two-dimensional diagram, I'm going to be a little bit more rigorous. I'm going to go ahead and I'm going to use a ruler, for example, like so, and I'm also going to use a protractor. Okay, now let me begin by going ahead and drawing here two-dimensional space, like so. The x and y axes respectively. Okay, and then I have my next vector, or my first vector, I guess I should say, at a 45-degree angle. So I'm going to take my protractor here and line it up with the positive x-axis, like so, and then measuring over 45 degrees, that's about this point here. Okay, now I have to draw a vector that is 5 meters long. Okay, obviously I don't have enough board space in order to do that, so I'm going to set up a little scale. I'm going to say on my ruler here, on my meter stick, I'm going to say that 10 centimeters on my meter stick corresponds to 1 meter in the problem. So then therefore I have to draw the vector A here as 50 centimeters in length. All right, so doing so here at a 45-degree angle, I'm going to go from 10 to 60. That is then going to look like this. Like so. So right there is my vector A. Okay, now using the tail-to-tip method, I'm going to add to that then the vector B. The vector B, however, is at a 135-degree angle. So what I have to do is take my protractor again. Now I'm going to go ahead and position it right here at the tip of A, and I'm going to line up the edge of the protractor here such that it's pointing along the positive x-axis. And I'm going to go ahead and measure over 135 degrees. That's to about there. And then I have to draw the vector B here as 30 centimeters long. Okay, so doing so, I'm going to go from 40 to 10 here on my ruler, like so. Right there is the vector B. And then using a different color here, the resultant, the vector C, that's going to be drawn from the origin to where I end up. Once again, I'll use my ruler in order to do this. That will then look like this. All right, so lining this up carefully. There we go. Like so. Right there is my resultant, the vector C. Okay, now in order to find its magnitude, of course, what I have to do is I have to measure it. So doing so. All right, so I measure this out, and it turns out to be about 59 centimeters in length. So then therefore, using my scale, that's 5.9 meters as the answer. And then, secondly, in order to obtain its direction, so far the only means that I have available to me of determining that direction is by measuring it with my protractor. So going back to the origin like so, and then lining up my protractor, measuring over that angle right there, I'll go ahead and draw it like so. This angle right here is about 75 degrees. Now, of course, I'm being very careful here in order to measure out the lengths associated with all these vectors, measure out my angles, etc. But of course, everything that you saw me do here the last couple of minutes is prone to measuring error. So then therefore, how do I get around that problem? That is, how do I add the vectors together analytically? Well, in order to describe that, once again, we have to go through a little bit of mathematical background. So put aside the problem that we just did for a few minutes. We'll come back to it in a few minutes. Let me take you first of all through the necessary mathematical background that we need in order to add vectors together analytically. I'll begin by describing what are referred to as unit vectors. Okay, unit vectors have the same properties of ordinary vectors as we've seen so far, except for two things. Number one, by definition, unit vectors always have a magnitude of 1. That's what the word unit means. It means that we have a magnitude of 1. So in the problem that we just completed, this would then mean that the magnitude of a unit vector would be 1 meter. And then secondly, unit vectors always point in specific directions. So for example, there is a unit vector that defines the positive x direction, like so. This unit vector that defines the positive x direction is referred to in the following manner. We write the letter I, and then this little symbol above, like so. We pronounce this as I hat. I hat is the unit vector that points specifically in the positive x direction. However, in a textbook and also in lecture examples that you'll see in my notes, we always denote it instead by just simply using bold type. However, when you see me write I hat on the board, that specifically means or refers to the unit vector in the positive x direction. And then perpendicular to that, there is a second unit vector that refers to the positive y direction. Once again, it has a magnitude of 1. It's at a right angle with respect to I hat. This is referred to as j hat. So I hat and j hat are the unit vectors that we use to describe the x and y direction. Now, perpendicular to I hat and j hat in the third dimension, like so out of the board, think of this as the z direction. The unit vector that we always use to denote the z direction is referred to as k hat. However, for now, we're only taking a look at two-dimensional cases here, I hat and j hat, and that's perfectly fine. Now, whenever you write out a vector in two-dimensional space, you could always think of it as the addition of two other vectors. For example, so just drawing this by hand, let's say that I have the xy direction like so, and then right here is a vector A. This vector A has two things associated with it. It has a magnitude and it has a direction. However, we could always think of this vector here as being the resultant of two other vectors. In other words, two other vectors that are added together. One of those vectors specifically points along the positive x-axis, like so. And then the second of those two vectors points along the positive y-axis, like so. Notice that the addition of these two vectors here results in the vector A. What I end up with here, however, very simply, is a right triangle. The sides of the right triangle are referred to as the components of the vector A. The length of this component is referred to as a sub x. A sub x is the component of vector A that points in the x direction. The length or size of this component here is referred to as a sub y. So a sub x and a sub y are the lengths of the components of the vector A. Finding a sub x and finding a sub y using this right triangle just simply involves a little bit of basic trigonometry. For example, if we know what a is and we know what theta is, what trigonometric ratio would we use to find a sub x? Very simply, we would use cosine. So recall that the cosine of an angle is equal to the adjacent side divided by the hypotenuse. In this case, a sub x over a. So if you just cross multiply a little bit, a sub x is equal to a cosine theta. Similarly, we can find a sub y by using sine. Sine of theta is equal to the opposite side divided by the hypotenuse. So then therefore, if you cross multiply, the opposite side, a sub y, is the hypotenuse multiplied by the sine of the angle. So finding the components of a sub x and a sub y, is easy to do. The process, of course, can be done backwards if necessary. For example, if we already know a sub x and we already know a sub y, we would then just simply use a little bit of Pythagorean theorem to find a. Notice that a sub x squared plus a sub y squared is equal to a squared. We would then just simply take the square root, and we would then end up with a positive value because we're talking about a magnitude in order to find the magnitude of the vector a. So then therefore a would be equal to the following. And then knowing the components, if we needed to find the angle, we can once again use a little bit of tangent in this case to do so. Notice that the tangent of the angle theta is equal to the opposite side, a sub y, divided by the adjacent side, a sub x. So of course, all that we're doing here is a little bit of right triangle trigonometry, but now we're beginning to dress up that right triangle trigonometry in its full vector form. Incidentally here, however, how do you then write the vector a by using these components? Well, this is where the unit vectors come into play. So for example, take a look at this component here. The magnitude of this component is a sub x. However, the vector itself is a sub x multiplied by the unit vector I hat. Similarly, the length or magnitude of this component here is a sub y, but the vector itself is a sub y multiplied by j hat. Like so. Writing a vector in this manner, that is the vector a, is called breaking or resolving a vector into its components. Now, why do we find it necessary to do all of this? Why do we bother to break up vectors into their components? Well, now, watch what happens when I do, in fact, add two vectors together. So once again, this is just a generic example. I'll get back to the example on the top board in just a few minutes, but for now, let's say that right here, I have a vector A, and then right here is a vector B. And then each of these two vectors then have components, but before I draw those components, the resultant of these two vectors, a vector C, would be drawn like so. So off to the side, C is equal to A plus B. But now take a look at the vector A. The vector A, first of all, has a component here along the x-axis. This is a sub x. And then right here along the y-axis, right here is a sub y. So in component form, A is equal to a sub x I hat plus a sub y j hat. Okay, and then take a look at the vector B. The vector B also has components. Right here is b sub x. Right here is b sub y. So in component form, the vector B is b sub x I hat plus b sub y j hat. And now just look at the purple vector C all by itself. Right here, along the x-axis, is the component C sub x. Right here, along the y-axis, is the component C sub y. So in component form, the vector C is C sub x I hat plus C sub y j hat. But stare at the diagram for just a moment. Take a look at C sub x right here. What is C sub x also equal to? Well, notice that it's equal to A sub x plus B sub x. Similarly, take a look right here at C sub y. Notice that C sub y is equal to A sub y plus B sub y. This is how we add vectors together analytically. What we do is we break the vectors into their components and then just simply add the components together to get the resultant. Once we have the resultant, then we do a little bit of right triangle trigonometry to find the magnitude and direction of that resultant. So now that is the process here that we add vectors together analytically. Let's go ahead and take a look at the example still on the top board and add those two vectors A and B analytically using this method. Okay, so from the top board, let's take a look at the vector A. Okay, here's the vector A. It has a magnitude of 5 meters. Here are the components of the vector A, and then right here is the 45-degree angle. So then therefore in component form, the vector A would be first of all right here a sub x, which is the hypotenuse multiplied by the cosine of the angle. And then right here is a sub y, which is the hypotenuse multiplied by the sine of the angle. Like so, all in terms of meters. Make sure that you always write down the unit symbol associated with this problem. Okay, now I'm going to go ahead and multiply out on my calculator here in degree mode. In my calculator, 5 times the cosine of 45 and 5 times the sine of 45. So first of all, making sure that I'm in degree mode, and then I have 5 times cosine of 45, and then going out maybe 2 decimal spaces, this works out to be the following. So, same thing for the sine of 45. If you recall from basic trig, cosine and sine of 45 are the same thing. So this right here is also 3.54, like so. Okay, let me pause at this point to say something a little bit about significant figures. Recall the horrors of significant figures, for example, say in a chemistry course. What is my policy regarding significant figures here in this class? Frankly, I don't care. Significant figures are important when you actually do experimental science, but what we're doing here is, of course, learning the basics. So then therefore, even though experimental science involves very rigorously the use of significant figures for problems that I do here in lecture, for examples that you do in homework and so forth, frankly, it's not that important. So then therefore, because of that, usually what I do is round off 1 or 2 decimal spaces. Good enough. That's perfectly fine. Okay, now let's take a look at the vector B, still from the top board. This has a magnitude of 3 meters, and it's at a 135-degree angle. So right here, like so, is, whoops, vector B, pointing into the second quadrant, excuse me. There we go, like so. Right here is the 135-degree angle, and then right here would be B sub x, and right here is B sub y. Here's how you write the vector B in component form. Okay, first of all, we have the adjacent side of the triangle here, which is equal to hypotenuse multiplied by cosine. And then we have, with the other side of the triangle right here, is B sub y, that's the opposite side. This is equal to hypotenuse multiplied by sine. Once again, all in terms of meters. Okay, now I'm going to go ahead and multiply this out on my calculator. So first of all, 3 times the cosine of 135. That comes out to be about negative 2.12 or so. And then 3 times sine of 135. It's the same number. In this case, however, it's just positive 2.12 in terms of meters. Notice how the negative signs here take care of themselves. The negative signs take care of themselves if you always measure the angle with respect to the positive x-axis. So by taking the cosine of that angle, 135 degrees, I pick up the negative sign that is necessary here associated with b sub x. And now what I have to do is add these two vectors together analytically, just add the components together to now get the resultant, that is the vector c. Okay, so then therefore the x component of the vector c is going to be this 3.54 plus this negative 2.12. So 3.54 minus 2.12, and that comes out to be 1.42. And then I get the y component here of the resultant, the vector c, by adding together this 3.54 and this 2.12. So 3.54 plus positive 2.12, and that comes out to be 5.66, like so. So in component form, this is the vector c, and now just by itself, I can then draw the vector c in the following way. Okay, so pointing into the first quadrant like so is the vector C. We know it's a first quadrant vector because it has a positive x component here of 1.42 and a positive y component here like so of 5.66. Now I'll just go ahead and use a little bit of Pythagorean theorem here to find the magnitude of the vector C. All right, so doing so, 1.42 squared plus 5.66 squared, take the square root of all of that, and I end up here with the magnitude as about 5.84 meters, like so. Compare this number here, which was found analytically, with what I did with measuring up on the top board. So my measurement was pretty good, but of course it was off a little bit. It was off a little bit because I was not adding the vectors together analytically on the top board. I was doing so graphically, which is prone to measuring error. Even though I have been rounding off my numbers here a little bit as I've gone through the procedure of adding the vectors together analytically on the bottom board, this answer here is much more precise than that answer on the top board. And then we have here the angle, like so. Let's just call the angle theta. What I'm going to do is just a little bit of inverse tangent on my calculator, the inverse tangent of 5.66 and 1.42 in order to find then that angle. Okay, so inverse tangent then of the opposite side of the triangle, 5.66, divided by the adjacent side of 1.42, and this comes out to be about 76 degrees. It's actually 75.9 degrees, but good enough. I'll go ahead and round it off to 76 degrees. My measurement of the angle of 75 degrees on the top board was pretty good, but once again, this is a much more precise result when you add the vectors together analytically. Okay, so to finish this lecture here on two-dimensional vector addition, let me just go ahead and conclude with another basic example. So go ahead and copy down that next example into your notes while I erase the board. In this last example, we are already given the two vectors in component form. Notice how they're written, by the way, in the lecture examples Word document using bold type for I hat and j hat, the unit vectors. When you are given vectors that are already in component form, adding them together is trivial. So here we are. So in this last example here, A is 5i hat plus 4j hat, and then vector B is negative 8i hat plus 2j hat. There are no units associated with these two vectors. That's fine for this ordinary mathematical example. And now let's go ahead and find the resultant, the vector C, by just adding the components together. So 5 plus negative 8 is negative 3, and then 4 plus 2 is 6. So we end up with a vector here that is into the second quadrant. We have a negative x component here and a positive y component. So let's go ahead now and find the magnitude here of the vector C. We'll do so by just doing a little bit of Pythagorean theorem. So 3 squared plus 6 squared, add that together to get 45, take the square root of that, and that ultimately ends up being about 6.7. But when it comes to the direction here, because this vector is a second quadrant vector, we're going to have to be a little bit careful. So for example, the vector C here in this problem roughly looks something like this, where this right here is 3 to the left-hand side, and this right here is 6 in this direction. Let's go ahead now and find, with respect to the positive x-axis, this angle here, call it the angle theta. Once again, we'll do so by using a little bit of tangent. So tangent of theta is equal to the opposite side 6 divided by the adjacent side here 3, but keep in mind that the 3 points to the left-hand side. So then therefore it's negative. So now what I have to do is take the inverse tangent of 6 over negative 3. So inverse tangent of 6 over negative 3 on my calculator display works out to be about the following, about negative 63 degrees. If you just simply left your answer like this, it would be counted as wrong. The 63-degree angle that we just found is actually this angle right here on the diagram, 63 degrees in this direction like so, measured with respect to the negative x-axis. That's not the angle that we want. Obviously, we want its supplement. The angle theta would be found by adding this to 180 degrees. So then therefore 180 minus 63 works out to be 117 degrees as the answer. You must be quadrant specific when finding the angle associated with a vector. So for example, in this problem, your calculator doesn't know the difference between, say, second quadrant and fourth quadrant. But you do, and you have to adjust for that accordingly, as I did here in this example. Notice in this last example that it actually wasn't necessary for me to draw out the tail-to-tip method of vector addition in order to find the resultant, but I still encourage you to do so, but you can just simply sketch things by hand when doing so. With a little bit of practice, showing how these vectors add together by using the tail-to-tip method is trivial. So here's what this diagram ultimately looks like for this problem. Okay, so obviously I'm just drawing this rough at this point. It's not necessary for me to use a ruler and protractor when doing this. So we have, first of all, the vector A. The vector A points into the first quadrant. So it's like over 5 and up 4. It roughly looks something like that, like so. And then we add to that the vector B. The vector B points into the second quadrant. So it's like negative 8 and then up 2. It kind of roughly looks something like this, like so. And then the resultant, the vector C on the board, that then looks about like this. Perhaps a little bit of a better diagram than what I drew for the vector C all by itself up on the top board. But now pantomizing this using the tail-to-tip method of vector addition, pantomiming that is, we have here A plus B like so is equal to C. Okay, that concludes this lecture on two-dimensional vector addition.